7.5 is modeling data using log functions. So we looked at graphs of log functions in the last section. Now we're trying to apply that to data, see what you can either interpolate or extrapolate from data when you're given it. So it says the equation of the log regression function can be written as y is equal to a constant plus your multiplier times natural log of x. Most graphing calculators and spreadsheets provide the equation of the log regression function in the form y is equal to a plus b ln x. So this is the general form that you're going to find it in. You can manipulate that equation if you want to look at it as an exponent. So if I move my a over and then divide by b, I have y minus a divided by b is equal to the natural log of x. To go from a log to an exponent, the x stays there. For natural log, the opposite of that is my e value, that 2.14, I think. I can't remember exactly what the value is. So that would be e to the power of y minus a over b. That's how you would find x, or that's one way of finding x. So example 1 says, in February 2004, Mark Zuckerberg launched Facebook from his Harvard dorm. Facebook had 1 million registered users by December of that year, and it has been growing rapidly ever since. So the A part for this wants us to create a scatter plot that relates the date in the number of months, that's our dependent variable, to the number of registered users of Facebook, which is our independent variable. So it's a little confusing looking at it in the chart this way, because usually your first row is your x and your second row is your y. But for purposes of this question, they're setting it up so that your dependent variable, your y values, is the number of months. So that depends on how many users you're looking at, if you want to think of it as a dependent-independent statement. So these are our y's and these are our x's. So to create a scatter plot for this, then you're going to do what we've done in the other section. So go into your excuse me, your list. So the stat, edit, and you're into the list here, and enter in your data for these. So I'm just going to pause as I'm doing that so I don't use up recording time. Okay, so the data is entered in here. We can graph it. We're probably going to have to change our window a little bit. Why are those graphs in there? I may have to change the stat plot's probably not on. There we go. So now let's graph it. So we're going to zoom in a little bit. Where's zoom fit? I'm going the wrong way. I think the other way is. Oh, look at all those. Go to 0. Okay, why didn't it zoom in? Okay, I guess I'll just do it the old-fashioned way. So I know I'm going from, my x's are starting at 1, meaning 1 million, so let's go from, we can leave that at -10 to 650 will go up by 50. -10 to, how many months does it go up to? So let's go up to 90. Go up by 10s. Okay, now let's graph the, there we go. So, by the looks of that, the data appears to be the model of a log function. It's increasing from quadrant 4 to quadrant 1, where our values are getting higher. Here it looks like it's just on the line there, so if we went past the 0 mark, then we'd be you could see how it would be increasing. It'll get closer and closer and closer to 0, but not cross that on the y. So because it's an increasing function, then we know our a is greater than 0. So we can draw this on here. I'm going to move my, oops. Oh, okay. So when you go to draw this on here, and I'm not going to draw it all, you can do that. I'll just, on on this side, this is going to be your months since it launched. So you can go up by tens here. And then across the bottom, then of course you're going to have your registered users. And those of course are in the millions. So across the bottom here, you can go 100, 2, 3, 4, 5, and 6. And then you would plot your data. So your data, and like I said, I'm not going to plot all the points just to save us a little bit of time, tends to be going sort of like this, if you were to draw the line. And it kind of continues up. So the data here appears to be logarithmic, just from its shape, and it is increasing from quadrant 4 to quadrant 1. Therefore, we would assume A is positive. So it says use the data to determine the equation of the logarithmic regression function for time in months as a function of the number of registered users. Remember to enter the data into L1 and L2 first. So we've already done that. So if we want to do our line again, we go into Stat, Calc, and we are doing the log regression. Oh, I went too far. It should be right there. Okay, just have to pause for a sec. Okay, so we've got our line 1, our line 2. We want to calculate. And these ones have my numbers backwards from what I had done. So, not sure what I did incorrectly because I must have some data entered in there wrong. So I have on mine from when I did it before that I had 5.882. And B is equal to 10.833. So I'm just going to pause and see what I've done wrong for my data, that it's not working. Okay, I found my mistake. I had put 3,000 instead of 300 into my data, so that threw everything off there. So that is the correct values. So 5.882 is our A, 8882, and then 10.8333 is our y. So the equation would be y is equal to 5.8882 plus 10.8333 natural log of x. So the next question says, determine the number of months and date when Facebook first surpassed 275 million registered users. So on the calculator, because the user amount is our X, registered users is our X, so you can just do that value function. So I can go second calc value. Oh, I need my, whenever you do this, you always have to put in your line first. So it was y is equal to 5.88882 plus 10.8333. Oops. Oh, too far. Your line of x, natural log of mean of x. Okay, so there you go, you've got the equation entered. So now you can, well, you could graph it if you want, but let's just go to calculating. So calculate, I want when my x is equal to, so I'm on the wrong paper here, x is equal to 275 million users. So y is equal to 66.7, so basically 67 months. Okay, so to use this by the formula, I was just trying to read my notes. To use the formula then, you have y is equal to 5.888. I think there was a 2 in there, but that's okay. Plus 10.833 natural log of x. So if you substitute in there, y is equal to 5.888 plus 10.833 natural log of 275. So if you do that on your calculator, it says 67.7 months, so same thing, 67 months, which would be 5 years and 7 months. I'm just going to flip over to the back page because this is actually one of the questions in your textbook. So it's on page 498. So I'm just going to go through and answer the rest of the questions. So the C part for this asks, sorry, not the C part. No, I made up a question here, or I found a different question. So we're still going to flip to the back of the book, or back page here, just so I can, just for you to do a little bit more kind of work using this. So if we wanted to predict how many registered users did Facebook have 40 months after its launch date? So what this is asking then is, what is your X value when Y is equal to 40? So this is easy to do on your calculator, because on your calculator then all you need to do is put Y is equal to 40 and then do your intersect to see where the two lines intersect. So if I put y is equal to 40, oops, 40, graph it. I want to calculate intersect, so that's 5. So first graph, enter, second graph, enter, yes. And it tells you it's at 23.3. So there would have been so 40 months in, so that's what, 3.5 years in, there were 23.3 million users. If you had to do this by hand, we would have 40 is equal to 5.888 plus 10.833 natural log of x. So the first thing we do would be subtract that 5.88 from both sides. So you're left with 34.112. So 34.112 is equal to 10.833 natural log of x. So then from there, your next step is going to be to calculate by dividing out that 10.833. So if I divide here, so what I'm left with then is 3.149 is equal to natural log of x. So now if I want to change this to solve it, I need to change it into exponential value. So my x is equal to e to the power of 3.149. So you can do that on your calculator. I can just never remember where the e value is. There it is, e to the x right above the natural log button. So I do second function e, oh, I better quit this. Second function e to the 3.149, enter, 23.33. So x is equal to 23.3. So you get the same thing. This is just to show you how you would calculate going from natural log to exponential. Okay, so your data is in, and we do our calculation. Number 9, enter. So we have A is equal to 44.393, B is equal to negative 8.358. So that makes our equation. And you have to be really careful when you're entering these things. I had one number off in both of those lists and it totally throws off your data. So enter in your data and then check it over. So we have y is equal to 44.393 plus, I guess we don't put a plus, we'll put a minus. 8.358 natural log of x. So that's the equation. B part says determine the time for an average person to metabolize 50% of the caffeine in his or her bloodstream. Round your answer to the nearest tenth of an hour. So 50%, if we started at 100%, then we want to know, or sorry, if we had started at 200 milligrams, then we want to know 50% of that, so at 100 milligrams. So we have to put in our y equals. So y is equal to 44.393 minus 8.358 natural log of x. And we want to know when this is at oh, sorry. I was thinking the other way. So what we need to do then is we want to then, well, we can graph it. And we can then calculate. Maybe. Oh, it's still drawing it. So I want to calculate. There we go. The value, so when x is equal to 100 milligrams, .9, so y is equal to 5.9 hours. C part says Paula drank a cup of coffee which contained 200 milligrams of caffeine at 10 a.m. How much caffeine will be in her bloodstream at 9 p.m. that evening? Round your answer to the nearest milligram. So we want to know what is the milligram. So we want to know what is x when y is equal to, so if she starts at 10, at 9 o'clock then, that's going to be 11 hours later. So this is just the y equals. Y equals 11. Graph it, and then we want to calculate the intersect. I'm confusing it. I tried to do too many things at the same time. So second, I want intersect, so 5, enter, enter, enter. And so at 54.3. So 11 hours later, she'll have 54.3 milligrams left in her system. So our summary here. A log function may be a good model for a set of data if the points on a scatter plot form an increasing or decreasing curve, where the domain is restricted to the set of positive real numbers. So that's really when we use it. When your domain is restricted to positive real numbers, that's one of the situations where a log function comes in handy. The general form of the log regression is y is equal to the constant plus the multiplier times the natural log of x. Most graphing calculators and your spreadsheets, we don't do the spreadsheets, they take more work, provide the equation for that log regression function. A log curve of best fit can be used to predict values that are not recorded or plotted. Predictions can be made by reading values from the curve of best fit on a scatter plot or by using the equation. Okay, that's it for this section and for this chapter. Good luck with the questions.